This might sound complicated, but stick around, and I'll break it down for you. First, let's get some context. The PBR theorem was introduced in 2012 by Matthew Pusey, Jonathan Barrett, and Terry Rudolph. It's a no-go theorem in quantum foundations. Essentially, it tackles the core question of what quantum states actually represent in reality. Now, in the realm of quantum mechanics, there are these things called hidden variable theories. Some scientists believe these hidden variables could explain the seemingly random behaviors of quantum particles. Two main interpretations exist for quantum states in this context: ontic and epistemic. Ontic states represent a direct correspondence to reality, while epistemic states are about our knowledge or incomplete information about reality. So, what does the PBR theorem say? It declares that pure quantum states must be ontic. This means they correspond directly to states of reality. So, if you were thinking quantum states were just about probabilities or incomplete information, the PBR theorem says, nope, they're the real deal. How does this fit with other famous no-go theorems like Bell's theorem and the Bell-Cochin-Specker theorem? Well, Bell's theorem rules out local hidden variable theories, and the Bell-Cochin-Specker theorem rules out non-contextual hidden variable theories. The PBR theorem, similarly, rules out preparation-independent hidden variable theories. This means that quantum states that are prepared independently must have independent descriptions in hidden variables. The significance of this theorem was highlighted by theoretical physicist Anthony Valentini. He called it the most important general theorem relating to the foundations of quantum mechanics since Bell's theorem. The PBR theorem first appeared as an arXiv preprint and was later published in Nature Physics. In simpler terms, the PBR theorem shows that any model interpreting quantum states as mere information about an objective physical state can't match the predictions of quantum theory. PBR theorem challenges the shut up and calculate approach, which has been a popular stance among physicists for a long time. This approach suggests that we should use quantum mechanics to make predictions without worrying about the underlying reality. But the PBR theorem says, hold on a minute. It asserts that if the quantum state merely represents information about an underlying physical state of a system, then different quantum states must correspond to different physical states. This means that quantum states are not just about probabilities or our knowledge of a system. They have a real physical existence. Are quantum states real, or are they just mathematical tools? But there's more to the story. A common question that arises is the PBR theorem only applicable in two dimensions? The answer is a resounding no. The PBR theorem is not confined to the simplicity of two-dimensional systems. Its reach extends far beyond, applying to quantum systems of any dimension. The theorem asserts that if a quantum state merely represents information about an underlying physical state, then different quantum states must correspond to different physical states. This statement holds true regardless of the dimensionality of the system. Whether we are dealing with a two-dimensional spin system or a multi-dimensional quantum field, the PBR theorem stands firm. How does this interpretation challenge the classical understanding of quantum mechanics? Firstly, let's understand what it means to interpret the quantum state statistically. In classical physics, the state of a system is often considered a complete description of its physical reality. However, in quantum mechanics, the wave function or quantum state is frequently seen as a tool for predicting probabilities of different outcomes, rather than a direct representation of reality. Here's where the PBR theorem shakes things up. According to the theorem, if the quantum state were merely a statistical tool, then different quantum states would correspond to overlapping distributions of underlying physical states. In simpler terms, you could have different quantum states that describe the same underlying reality. But the PBR theorem argues against this. It suggests that different quantum states must correspond to different physical realities. This statistical interpretation challenges the classical viewpoint, where the state of a system is a direct reflection of its physical properties. Now the various experiments conducted to test the Pusey-Barrett-Rudolph PBR theorem. To begin with, let's look at the experimental setups. Researchers have employed advanced quantum systems, such as entangled photons and superconducting qubits, to test the predictions of the PBR theorem. These setups are meticulously designed to isolate quantum states and measure their properties with high precision. The goal is to determine whether the quantum states correspond to real physical states as suggested by the PBR theorem. Next, we examine the methodologies used in these experiments. One common approach involves preparing pairs of quantum systems in specific states and performing measurements to detect correlations. By comparing the experimental results with the theoretical predictions of the PBR theorem, researchers can assess the validity of the theorem. These methodologies often require sophisticated equipment and precise control over quantum states, highlighting the complexity of experimental quantum mechanics. Now, let's discuss the results of these experiments. Many experiments have provided strong evidence supporting the PBR theorem, showing that quantum states do indeed correspond to real physical states. However, some results have also raised questions and sparked further debate, indicating that our understanding of quantum mechanics is still evolving. These mixed results underscore the importance of continued research and experimentation in this field. Instead, the theorem suggests that the quantum state must correspond to a real physical state. First and foremost, the PBR theorem compels physicists and researchers to reevaluate existing interpretations of quantum mechanics. Traditional interpretations like the Copenhagen interpretation, which treats the wave function as a tool for prediction, may now seem insufficient. The theorem pushes us to consider that quantum states have a direct link to physical reality, urging a shift in our conceptual framework. Moreover, the PBR theorem has sparked much debate and further research into the interpretation of quantum mechanics. Scholars are now investigating alternative interpretations such as objective collapse models, many worlds, and even entirely new frameworks that might better align with the theorem's implications. This ongoing research is crucial, as it may lead to groundbreaking discoveries that could redefine our understanding of the quantum world. The theorem also has practical implications for quantum computing and quantum information theory. By asserting that quantum states reflect real physical states, the PBR theorem could influence the development of more accurate quantum algorithms and error correction methods, potentially accelerating advancements in these cutting-edge fields. In conclusion, the Pusey-Barrett-Rudolph theorem has profound implications for our understanding of quantum mechanics. It challenges us to rethink the nature of quantum states and their role in the fabric of reality. As we continue to explore and experiment, the PBR theorem will undoubtedly remain a cornerstone in the ongoing quest to unravel the mysteries of the quantum world.